Hello. In today's discussion, we're going to be using the standard normal curve that we dealt with in the prior topic and using it to calculate some probabilities and some application scenarios. So, like I said in the prior lesson, we found the areas under the curve of the standard normal if given a specific z-score. Today, we will be given application scenarios. So we must first convert to a z-score and then repeat what we conducted in the prior lesson. So as an example, say that the number of visitors to a movie theater in any given day has an average of 500 and a standard deviation of 100. State the z-score, draw the standard normal curve and the area to the left for a day with 600 visitors. So what we're really calculating is what's the probability that the number of visitors we get in a day is going to be less than 600. So our regular normal curve is centered about 500. One standard deviation to the right is an extra 100, so now we're at 600. We want to know what's the probability we get less than 600 people at that movie theater in a day. In order to calculate the z-score, what I need to do is take my measured value, subtract it from my mean, and then divide by my standard deviation. In this case, that'll be 600 minus 500 divided by 100. And that's going to be 100 divided by 100, which tells me that my z-score is 1. Because it's positive, I'm to the right, I'm above, I'm 1 standard deviation above the mean. So my standard normal curve would look like this. 0 is where 500 used to be because it is 0 standard deviations away from the mean because it is on the mean. 600 is right here at 1. So my picture really looks like this. What's the probability that I am less than 1 standard deviation away from me? So less than positive 1, to the left of positive 1. And in order to calculate this probability, before technology, we would have to look up the probability corresponding to that z-score of 1 in a table. So the takeaway is this: to calculate probabilities for normal distributions, simply we're going to convert to a z-score and then use the standard normal curve. So its picture looks like this. If you look, the actual picture doesn't look any different. The only thing that changed was the scale. I want to find the probability of having a z-score less than 1. That's the exact same as trying to find a probability that the measured number of people visiting a theater is less than 600 as long as our mean is 500 and our standard deviation is 100. In order to actually calculate this probability, we would have to look it up in a standard normal table, or because what we discovered yesterday, I can use normal CDF. My far left bound, just pick a number way to the left. We said negative 1,000. Actually, honestly, like negative of probably 10 would be far enough. All the way, our right bound is 1. Our mean is 0, and our standard deviation is 1. Just to show what that would be, we know this from the empirical rule, but just to verify that it's doing the exact same thing using our calculator, normal CDF, negative 1,000, comma 0, comma, oh no, our right bound is 1, 0, comma 1, and we get our 84% that we're used to for less than 1, or left of 1. So here you go. An example of doing this. So a survey indicates that people use their cell phones on average 1.5 years before buying a new one. The standard deviation is 1/4 of a year. A cell phone user is selected at random. Find the probability that the user will use their current phone for less than 1 year before buying a new one. Assume that the variable is normally distributed. So we first can find a z-score. Our measured value in this case is 1 minus 1.5 divided by 0.25. That's negative 0.5 divided by 0.25, and that's negative 2. So we take this, we really wanted to know less than 1. That's the exact same as saying left of negative 2 for our standard normal. Now, in order to calculate the probability, we just use normal CDF, far left bound, negative 1,000, all the way up to negative 2. Mean is 0, standard deviation is 1. Lower is negative 1,000. Honestly, negative 100 would have been fine. The upper was negative 2. And run it. Probability is going to be about 2.3%, 0.023. About 2.3% chance that someone is going to trade in their phone before a year. And companies like Verizon and Apple and AT&T and T-Mobile are going to care about that. Another example, the ACT has determined that the average score on the math portion is a 21 with a standard deviation of 5. What's the probability that a random score is more than 30? So calculate the z-score first. This is going to be, so more than 30, so 30 minus 21 all over standard deviation of 5. So this would be 9 divided by 5. That's 1.8. We want more than 30. In this case, if I drew out what the actual picture looks like, 25 and the standard deviations, we said 5, so this would be 26, then 31. 30, be right about here, which makes sense because for my standard normal, this is 0, this is 1, this is 2. 1.8 would be right there, and I want to be more than 30, so I'm going to be in there. I use normal CDF now. Normal CDF. My left bound is 1.8 all the way up to 1,000. 0, 1. So lower bound 1.8, upper bound big number, mean 0, standard deviation 1, run it, about a 3.6% chance. You're going to get a score of more than 30 on the math portion. What about a score between 16 and 28? Well, in this case, I have to calculate two z-scores. So 16 would be 16 minus, average was 21, standard deviation is 5, negative 5 divided by 5. So that has a z-score of negative 1, which makes sense because each of these were 5. So this is 16, this is 11, this is 26, this is 31. So I'm really trying to find it in between this and then 28. So somewhere there. I want to find probability being in there. Second z-score, 28 minus 21 divided by 5. That's going to be 7 divided by 5, which is 1.4. Now, just to show what the standard, so this would be 0, this would be 1, this would be 2, this would be negative 1, this would be negative 2. I'm really trying to find it in between negative 1 all the way up to this right here, 1.4. So normal CDF. Lower is negative 1, upper is 1.4. My mean is 0, my standard deviation is 1. So we said lower is negative 1, so negative 1 up to 1.4 standard deviations with a mean of 0. Standard deviation is 1 because it's a standard normal. And the probability of being in between those two scores is a 76% likelihood, 0.76. And that's how you use standard normal. Convert it to a z-score, then you can use normal CDF. I'm going to give you a chance to try. A medical study was conducted and determined the average time spent sleeping is 6.1 hours with a standard deviation of 1 hour. Find the z-score in percent of people who get at least 7 hours of sleep. Think to yourself, at least, what does that mean? That means equal to or more than 7. So pause the video now, come back and see how you did. Z-score, as you can tell, well, 1 hour is a standard deviation of 1. So 7.1 is going to be 1 standard deviation. We want to be at 7, so we're just less than 1. My standard normal, so this would be 0. This right here, 6.1 would be at the mean. So this should be 6.1, then 7.1, then 8.1, then 9.1, and 5.1, and 4.1, and 3.1. So this would be 1, 2, 3, negative 1, negative 2, negative 3. We want to be at 7. 7 is going to be just less than 1 because 1 standard deviation corresponds to 7.1, so we're right in here. We want at least, so this is the picture that we're looking at. Z-score is 0.9. Turns out to be about an 82, 81.6% that we're going to get at least 7 hours of sleep. That doesn't seem right here. I can see this doesn't make sense. This needs to be the complement. That is a typo because that 81.6 is this part over here. So this was ran probably incorrectly. This should be normal. We'll do it right now. This right here is 81.6%. So that is incorrect. Let's do it right now. Normal CDF of 0.9 up to 100. I think it was ran the other way around. 0, 1. Let's verify a second. Distribution, normal CDF, 0.9 up to 1,000. Standard deviation's 1, mean is 0. Run it, yep, 18.4, which is the complement of that. Yep, so it was ran, this was the 81.6 like I thought. Just that's why you draw the pictures. So 18.4% chance you're going to get at least 7. What was stated before was at most 7. So this should be 18.4% for 7 or more hours of sleep. There is a little bit of an unnecessary step that we've been taking, and that's because when this was invented and going to standard normals, is because we had to convert it to a z-score because we only had normal tables. We couldn't have tables for all these different means and standard deviations. So what we did is we converted it to a z-score and then used z-tables. But in reality, with computers and calculators, we really don't need to convert to a z-score. This is only required when we were using standard normal tables, which was the only option 20 plus years ago. So instead, we can simply use normal CDF, left bound, right bound, and then state the actual mean and the actual standard deviation. So we're going to do 2 quick examples of that. So find the following probabilities by using the calculator and not first converting to a z-score. So example, let's say some batter in the major league, in the MLB, he has a lifetime batting average of .262, which means he gets a hit about 26% of the time. What's the likelihood maybe this year his batting average is at least 27% if the standard deviation is 9%, 0.09. So we can simply do normal CDF, left bound is 0.27, right bounds pick a large number for this scenario. For this scenario, 1,000 is a large number. Our average actually is 0.262. Our mean is 0.262. Our standard deviation is 0.09. You'll see we don't need to convert to a z-score anymore because we're using technology. It does it for us really. So I grab my calculator and I run normal CDF 0.262. Pick a large number for the scenario. 1,000 is very large for this scenario. Oh, sorry, my lower bound is not 0.262. My average is that. My lower bound is 0.27. My mean is 0.262, and my standard deviation is 0.09. Let's just verify that real quick. Yep. And what's the likelihood he has a batting average of 27% or more this year? About a 46% chance, 46.4. So 0.464. Second scenario. Average total cholesterol. So this is used for like health screenings in order to give health benefits or set insurance premiums. Looks like the average female between 35 to 44 has an average cholesterol of 195. Standard deviation is 37.7. What's the percent of people that have a cholesterol between 190 and 215? They might, determine these bands that are considered to be healthy maybe. Lower bound's 190, upper bound is 215. The mean is 195. And standard deviation is 37.7. So grab my calculator. Lower we said was 195. Upper was, lower is 190. I keep doing the mean. Upper bound is 215. We want to be in between those two cholesterol levels. The average is 195, and standard deviation is 37.7. How many women would we expect to fall in that range? About 25%, 0.255. So going forward, you do not have to convert to a z-score. You can simply just use normal CDF with the actual mean and the actual standard deviation. Just wanted to show examples of using it to talk about what we had really before technology, so you can appreciate what the technology is doing. I can give you one to try. Find the following probability by using the calculator and not first converting to a z-score. So the average SAT writing score is 488, standard deviation is 114. What's the likelihood someone's going to score between a 200 and a 450? Once you found that probability, imagine if 500 people took the SAT in one sitting, how many would you expect to get a writing score between 200 and 450? Pause the video now, come back and see how you did. Here we go. Situation A turns out to be about a 36% likelihood that somebody's going to score in that range. How many would we expect then if 500 people took it? It's about 182. Where did we get that? Well, we simply take 0.3637 and multiply it by 500. And that's where you're going to get the actual amount of people that would get that score in that sitting. And that is it for today. Thank you very much and have a good day.